Hey guys, welcome back to class. And this week we're going to be talking about the ideal gas laws. I want to start out by talking about the units for these laws. Now, the units we're going to talk about are pressure, temperature, volume, which those three we should already know, and then the new unit of moles. We're going to talk about that. Um, and actually, moles isn't too difficult too difficult to concept, but it is new, so it's going to be the one I'm going to be focusing on the most. This is how you write the units for moles. You just drop the E. It's pretty simple. Um, Now the units for pressure are ATM, pascals, kilopascals, torr, millimeters of mercury. Those are the ones we're going to be seeing. For temperature, it's Celsius and Fahrenheit are the ones we're used to. The one we're going to use in the calculations is going to be Kelvin, and there's a reason for that. We'll get into it. Volume, the ones you're most often going to see are liters, milliliters, centimeters, and meters. Centimeters cubed and meters cubed. Now for pressure. Well, pressure is the definition is the amount of force that's exerted on an object. Now that's a basic definition. The better definition is actually in the form of an equation, which is force divided by area. Now I chose this picture of the ballerina on her tiptoes because my face is getting in the way. I chose this picture of the ballerina on her tiptoes because let's say the ballerina weighs about 80 pounds or 100 pounds. Um, if she goes on her tiptoes, she still has the same force, right? Weight is just the force you're applying to the earth. If you get on your tiptoes, you still have the same weight. If I step on a scale, I don't weigh less just because I go on my tiptoes on the scale, right? She's applying the same force, but her toes are touching less of the earth. There's less surface area touching, and that's why her toes hurt when she goes on on their toes, right? Because there's less area touching the floor, but it's the same amount of force, right? And that's the increased pressure, right? You feel more pressure on your toe because you're applying more pressure to the earth by applying the same force but over a smaller area. The units we use for pressure are ATM, torr, and pascals. I went over another few in the intro slide, but these are the main ones. The way they relate are 1 ATM is equal to 760 torr, which is also equal to 101,325 pascals. Now, pascals is a really big number. What we like to use instead is kilopascals. So about 101 kilopascals, kPa. 101.3. Right, that's the same number as this, but with the kilo prefix. Now, volume is defined as the amount of space that stuff occupies. So if you can see here in this picture, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 gas molecules. And on the right, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have the same amount of molecules in both pictures, but these 10 gas molecules are taking up less space, so they have a smaller volume. And this picture that we have, we're gonna be using these a lot with the ideal gas laws. It's called a collapsible piston. The units for volume that we're going to use are milliliters, liters, and centimeters cubed. Now, the things we talked about in class, the ways to find volume are if you have a regularly shaped object, you can take its width, multiply by its length, and multiply by its height. That'll give you the volume of a cube or a box. Another way, if you have an irregularly shaped item like a pebble, you can't just measure the sides. What you do is you put them in water, and the amount of water that gets displaced or moved up, that's the volume of the pebble. Because in both these, I have the same amount of water on the left as I do on the right. The reason why the water level is higher is because now I have this pebble in here, which is also taking up space and pushing the water up. However much water got moved up from here to here, that's the volume of the pebble. Right, so there's different ways to find volume. Now, temperature is one we're very used to, but actually we don't know the definition of quite yet. The definition of temperature is the average kinetic energy of molecules within a substance. And there are three different units that we usually use are Fahrenheit, Celsius, and Kelvin. The two that you'll notice recognize are Fahrenheit and Celsius. The unfortunate part about these measurements or units for temperature is that they have a negative value. Once you get past zero, you actually have negative numbers here. And when you put these negative numbers in calculations, they do different things than what these positive numbers do in calculations. So what we what we do in science is we like to ignore Celsius and Fahrenheit, and we like to use Kelvin for whenever we're using calculations, because what that does is it ignores the fact that you have negative numbers, because Kelvin has no negative numbers. Kelvin scale, the lowest possible temperature is 0, which is absolute 0 when everything stops moving. So just know that we're going to be using Kelvin in our calculations. Now, the new unit is moles, and what a mole is, it's just a counting unit for the number 6.022 times 10 to the 23rd. It's a counting unit just like a dozen is a counting unit for 12, right? If I have 1 dozen, I have 12. If I have 1 dozen donuts, well, I have 12 donuts. If I have 2 dozen donuts, I have 12 and 24 donuts. Right? I'm just counting with the word dozen. If I have 1.5 dozen donuts, we'll have 12 donuts plus 6 more, plus half a dozen. If I have 1.75 donuts, or dozen donuts, that means I have 12 plus 9 more, right? That's 3/4 of a dozen. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Now, a dozen is equal to 12 things, just like a mole is equal to 602 hexillion things, right? That's a whole bunch of zeros. So you have 602.02 times 10 to the 23rd. As scientists, that's the number we like to write. Now, what does a mole of tin look like? A mole of tin looks like this. A mole of carbon is this much. There's 6.02 times 10 to the 23rd tin molecules in this picture. There's also 6.02 times 10 to the 23rd carbon molecules in this picture. And there's 6.02 times 10 to the 23rd copper molecules in this picture, right? But all this talk about donuts and moles got me thinking, how far can 1 mole of donuts reach if you stack them end on end? And I started doing research, and I started doing more research. And I started realizing that a mole of donuts is actually a lot. What I did is I had to think about it. A donut is about 1.5 inches, right? And then I converted 1.5 inches to kilometers. And then I went from kilometers, I multiplied that by how many donuts would be in a mole, which is 6.02 times 10 to the 23rd. And I figured out that there would be this many zeros in the number, right? 19 zeros. And I have no idea how to say that. I can go 1,000, million, billion, trillion, but anything past that I really don't know. So then I looked up this chart, right? Now, so after trillion, you have quadrillion and quintillion. Well, this tells me number of zeros. If I have 18 zeros, I have 1 quintillion. But I have 19 zeros, so I actually have 10 quintillion. 10 in the tens place. So if I were to count this out, I would have 20 quintillion kilometers. That's how far I would reach, 20 quintillion. Now, how big is that number? Well, I tried to think of something that I knew was really big, right? Well, what's the size of our solar system? I looked up the size of our solar system, and our solar system is 287 billion kilometers, which is just under a trillion, right? It's 11 zeros. So if this is the size of our universe, is about here, and a mole of donuts would be about here, which is way more. It's it's a factor of 9 more. So that just shows you how big a mole actually is. A mole of donuts, I don't think you could really eat in one sitting. Some people probably could though. Now that's the end of what we're talking about today for the units of ideal gas laws. What I want you guys to know before you click on the test and get started, make sure you can define pressure, volume, temperature, and moles. And have a great day.